Hello and welcome to this talk on the Nyren-Kramers law for periodically forced bistable systems. So this talk is partly based on joint work with Barbara Gens and partly on work I did by myself during the lockdown. Let me start right away by showing you the system we're interested in. So it's a two-dimensional stochastic differential equation. The drift for the first variable x derives from a potential V0, which is a double well in x, like in the picture here, and periodic in y. The drift of y is a small parameter epsilon, and in addition we have independent white noise on both variables with a small parameter sigma in front. The question we are interested in is the following. So if we start somewhere in the left-hand potential well, what can we say on the law of the first hitting time of the bottom of the right-hand potential well? Let me recall a few well-known facts of the static case, meaning epsilon is 0 or the potential does not depend on y. Here's my notation for the curvatures of the potential at its stationary points. So first of all, using Dynkin's equation, you can obtain explicitly the expectation of the first hitting time of the right-hand potential well starting in some point x. That's because Dynkin's equation gives you an ODE of this as a function of x that you can solve. And in particular, if you start in the left-hand potential well and do Laplace asymptotics on this formula, you obtain the so-called Nyren-Kramers law. So it shows that the expected transition time is exponentially large in the barrier height between the starting minimum and the saddle, and there's a prefactor depending on the curvatures introduced here. Furthermore, Day has shown that the law of tau plus renormalized by its expectation converges to the law of an exponential variable of parameter 1 if sigma goes to 0. Now, this expectation is exponentially long, but it doesn't mean that the system spends a lot of time near the saddle. Actually, what it does is it does many failed attempts to cross the saddle, and the successful attempt in crossing is much shorter. So one way of describing this is the following, which was developed by Serrault, Guyader, Lelièvre and Malrieux. So what they do is they take points A and B close to the potential minima and start somewhere between A and the saddle. Then they look at the law of the first hitting time of B, conditioned on the fact that you hit B before A. And the result is that if you subtract a logarithmic term in sigma, you converge to the sum of a Gumbel random variable and a deterministic shift. So this shows that the actual transition takes a time of order log sigma inverse. Now, our system is not one-dimensional, so what is known in higher dimensions, you can always obtain the exponent of the expected transition time using large deviations, though the formula you obtain is not always very explicit, so this exponent is given as the solution of some variational problem. Now, in the gradient case, much more is known. In particular, the invariant measure is a Gibbs measure, and the process is reversible with respect to this invariant measure. And Nyren-Kramers law for the expectation of tau plus, as well as the fact that tau plus is asymptotically exponential, are known for these gradient systems, and there are basically two approaches that have been developed, one based on potential theory and the other based on semi-classical analysis. Now, our system is not gradient, and in the general case, much less is known, though you can prove that an invariant measure exists under some conditions. Its explicit form is not known in general, and the process is not reversible with respect to the invariant measure. Nevertheless, there have been some results. Boucher and Régnier did some formal computations that suggest a Nyren-Kramers law in some bistable situations. Landim, Mariani, and Seo developed non-reversible potential theory for this kind of systems, and in particular they were able to confirm the results by Boucher and Régnier for some particular systems for which you know the invariant measure explicitly. And also Le Petrec and Michel developed semi-classical analysis for this kind of systems with explicitly known invariant measure. Now returning to the system we're interested in that I recall here. With Barbara Gens, we looked at the first hitting time T0 of the saddle, or rather of the deterministic periodic orbit tracking the saddle, and obtained the following result. So again we have convergence of something to a Gumbel law, and this something is composed of three terms. So the first one is a convenient and explicitly known parametrization of the periodic orbit. Then you again have a logarithmic shift, and finally what is new here is that you have a constant times an integer valued random variable which is asymptotically geometric in the following sense here. The meaning of this variable here is that it tells you which is the period during which you cross some intermediate level between the starting well and the saddle. The parameter here is exponentially small in sigma, and it's related to the quasi-potential, but we did not try to determine it more precisely. And in fact, the expectation of T0 and also of T plus is related to the inverse of this parameter P of sigma. So what is missing here is sharp asymptotics on this quantity P of sigma, equivalently on these expectations. So that's the new result I want to present here. So I recall here my notations for the curvatures of the potential, and in addition I denote by r plus minus these quantities here, which are interpreted as transition weights between the potential wells in the static case. In fact, it is known that the leading eigenvalue of the generator of the static system, so meaning the first non-zero eigenvalue, is close to the sum of r plus and r minus. So here's my result. If I start somewhere in the left-hand potential well, then the expectation of the first hitting time of the right-hand potential well has the following form. So 2 pi over an integral involving the curvatures n exponential minus the barrier height here over sigma squared. And there's a multiplicative error which is complicated, but it's small if epsilon is large compared to the average of lambda 1 and small compared to the fourth root of this average. One thing to note here is that in the static case, if things do not depend on y, you recover the static Eirik-Kramers law. Now let me give you some intuition on why this result should be true. So it is expected that the process can be approximated by a two-state Markov jump process with transition weight r minus and r plus over epsilon. For this system you can explicitly compute the expectation of the transition time. It's given by this formula here where we use periodicity of the system in y. R minus, capital R minus, is the integral of the weight between two values of y. And it's easy to see that if epsilon is large enough, then this formula reduces to epsilon over the average of R minus, which is equivalent to the formula I just showed you. Now, on the other hand, if epsilon is much smaller than the minimal transition weight, you recover the instantaneous transition weight inverse. So, and in between things are more complicated because of stochastic resonance. But what this tells you is that we had this condition that epsilon should be larger than the average of lambda 1, this is to be expected because for small epsilon you have a different expression. On the other hand, the upper bound on epsilon with this power 1/4 is probably due just to technical difficulties. Now here's a short idea of the proof. So the proof is not based on the two-stage jump process. It is based on this non-reversible potential theory by Landi, Mariani and Seo I mentioned. And what this theory gives you in particular is a formula relating the expected first hitting time of a set B, starting on the boundary of a set A and with a particular measure. And this is related to the something called the capacity of the sets A and B, which obeys variational principles that allow you to obtain good bounds on the capacity. And in addition here you have H star is the committer of something called the adjoint process and integrated with respect to the invariant measure. So the main difficulty here is that we do not know explicitly the invariant measure, so we have to approximate it. There is, in this paper, they show that actually pi is related to the solution of a Hamilton-Jacobi equation, but it's hard to control error terms when trying to solve it. So rather what I did was to decompose pi in an eigenbasis of the static generator that gives you a system of infinitely many coupled ODEs that can be studied, and that gives you the result. And the strange condition on the upper bound of epsilon is actually due to technical difficulties in controlling the invariant measure. So that's all I wanted to say. Here are a few references, and thanks for watching.